We're going to look at properties of stars. This will be part one. And for the most part, we'll be applying things which you already know. Start by reviewing the magnitude scale. This is showing things from very bright to very dim. Usually I put the dim things up at the top and the bright things at the bottom so that the negative parts are headed downward, but that's the reverse of what we have here. So the very dimmest things are down at the bottom, magnitude plus 30. The Hubble Space Telescope can detect things, and some large Earth-based telescopes can detect those. Those are improving. They'll gradually see fainter and fainter things. Pluto has a magnitude of about plus 15. I've never seen Pluto. I've seen all the other, well, Pluto isn't a planet anymore, but you can see it through an amateur telescope. The binocular limit about plus 10. I've probably tested that pretty well. Naked eye limit about plus 6.0. And then brighter things, Sirius minus 1.4. Venus at its brightest minus 4.4. I think I've mentioned before, Venus is bright enough to cast a shadow on a light colored surface, so you can see your shadow. Full moon minus 12.6. The sun at minus 26.7. So these are apparent magnitudes. We don't have absolute magnitudes on here, and we're soon going to be thinking about a different measure of the brightness of stars. So, but just have those things in mind. Things we can learn from starlight, the surface temperature. And this will use the thermal radiation curve idea. We learned about this when we studied electromagnetic radiation, the graphs of light intensity versus wavelengths. Here are some perfect black body radiation curves. These are the theoretical curves. They don't behave the way things in nature do, although there are a few instances in nature where there have been nearly perfect thermal radiation curves produced by things.
Don't chew on this.
Had to rescue a blanket from my dog. Anyway, things you can see on here. These are all graphed on the same curve with the same axis vertically and horizontally. And something you can see is that as the temperature of something goes up, we've got one that's 4,500 Kelvin, one that's 6,000 Kelvin, and one that's 7,500 Kelvin. The peak of the curve moves towards shorter wavelengths, but the area under the curve gets very large very fast. And the area under that curve represents the total amount of energy given off per second per square meter of surface, or per unit of surface area. So that's something that happens. And that area under the curve, that total radiation given off, goes up with the fourth power of the temperature. That's the Stefan-Boltzmann law. Okay, now the next graph you're going to see has some features that make it less than a perfect thermal radiation curve, although you can still use it to determine the temperature, but you can determine some other things about the star. And this is the thermal radiation curve for an actual star. And what it has in it are a bunch of dips, a whole lot of dips, and those are caused by atoms and in some cases molecules in the atmosphere of the star, which the light from the star has to go through, and particular atoms absorb particular wavelengths. You can see here's an oxygen molecule here, another oxygen molecule there, and these cause, actually these are dips, whoops. I want to go back to that. Those are dips that are caused by oxygen molecules, plural, in the star's atmosphere. The light has to work its way through tens of thousands of miles of stellar atmosphere, and a lot of the wavelengths of light can be absorbed in that. And you can learn about the elements present in the star's atmosphere. Stars aren't solid bodies. They don't have some distinct dividing line between their atmosphere and the different layers of it. They're all stirred up all the time. And so the atmosphere is somewhat representative of what the entire star is made of. Although, for the most part, stars are hydrogen and helium. The other things show up in much smaller amounts. Okay, so the dips in that thermal radiation curve correspond to the light absorbed by certain elements and molecules. So we can learn elements present. And dips are part of what are called an absorption spectrum. We've learned about these before. So these are all emission spectra for different elements. And we've got sodium, calcium, strontium, cadmium, lithium, and mercury on there. So every element has its own fingerprint of wavelengths of light that it absorbs. And then this is an absorption spectrum, and it's black and white. It's a tiny part of the visible spectrum. The axis up here is in something called angstroms, and angstrom is a tenth of a nanometer. So this, if you converted this into nanometers, this part of the spectrum we're looking at goes from 530.5 nanometers up to about 532 nanometers. Actually, it goes a little farther to the left than 530.5, so probably close to 530. But this is only about a 2 nanometer range. This is an absorption spectrum from our sun. And you can see how crowded just that tiny 2 nanometer part is with absorption lines. And so pretty amazing. Some things that show up on here, you see a bunch of chemical symbols, like over on the far left, there's an Fe Roman numeral 1, and then there's an La Roman numeral number 2. The Roman numerals ones, and there's, let's see, I see a Roman numeral 1 for iron, that's Fe, chromium, that's Cr. Let's see, what else have we got? That's kind of it for the Roman numeral ones in this part of the spectrum, at least. But those are neutral atoms. And so they have as many electrons as they do protons. And so that's something. However, as soon as you strip off an electron from an atom, it'll have a new spectrum. And so there are a few places on here where you see Fe2s. There's an Fe2. That's a singly ionized hydrogen atom where it's lost one electron. Let's see, that was it for the Fe2s, I think. Here's a chromium 2, an La2. I haven't got all my chemical symbols memorized. Chromium 2 again, chromium 2, chromium 2. In this tiny part of the spectrum, quite a few absorption lines for singly ionized chromium. And we can tell that that exists in the sun's atmosphere. This is a complete absorption spectrum for the sun. The entire visible rainbow here, it starts down at the bottom, and you would move left to right along this bottom band, and then you'd move up one band and go all the way over to the left again and move left across here again. And you can see all the hundreds and hundreds of absorption lines, a tremendous amount of information that we can learn by studying the absorption spectra in the sun's spectrum. And so this is an amazing picture. Okay, which spectral lines exist also depends on the surface temperature of the star. And the reason for that is that if photons are too energetic, they can ionize atoms, in which case they may have a different set of spectral lines. So maybe there's a minimum temperature required for that chromium-2 or that iron-2. That's something that can happen. And then if photons aren't energetic enough, they may not excite the atoms, and so you might not see absorption lines from those particular atoms. And we've learned by studying lots of different stars, kind of a temperature scale that works for which spectral lines exist. And this is a chart that helps with that. Something you can see in here if we track down hydrogen here. Okay. Surface temperature of stars starts showing up at about 50,000 Kelvin. If they get too hot, you don't see much iron. Stars that are around probably 9,500 Kelvin, something like that, are very absorptive in hydrogen, and so you can see a lot of that. If the star is too cool, down around 3,000 Kelvin, you're not going to see absorption lines from iron. They disappear after a while. Similarly, if the star is too warm, like above 4,000 Kelvin, you won't see absorption lines from this thing right here, which is, whoops, didn't want to do that. This is titanium oxide. And so it can show up in the atmospheres of cool stars. It shows up other places as well. Turns out titanium oxide is the material that's in clown white, and it's also used in the white paint that NASA paints their rocket boosters with. There was one time, oh, it's been more than 10 years ago now, but for a short time they thought that they might have discovered a small asteroid orbiting the Earth, and that maybe we had a second moon. It was the first time they'd ever discovered anything other than our natural moon. But then when they studied the spectrum from it, they saw a spectrum of titanium oxide, and they realized, then they studied its orbit more, and they realized it was a spent booster from one of the Apollo moon missions. So it wasn't a natural satellite at all. But you can see, various temperatures here, like magnesium-2 and silicon-2 start showing up at a bit over 8,000 Kelvin, and you just don't see those at lower temperatures. But if you see a mixture of, say, magnesium-2 and silicon-2, you can put a minimum number on the surface temperature of the star, and then maybe if you also see helium-1, then you know that it's got to be above about 10,000. So, and it also, silicon-2 starts to disappear somewhere probably around 13,000. So you can kind of put numbers on it just by seeing what absorption lines there are. So it's an independent way of determining the temperature of a star. Something else we can learn from the starlight is luminosity. Now, to do that, which is a measure of the total power output of the star, this is including all wavelengths. When we talk about apparent magnitude and absolute magnitude, both of those are visual magnitudes. In fact, if we state it completely, we'd say absolute visual magnitude or apparent visual magnitude, but usually we just leave the visual out, but it's still only including visible light. But luminosity measures all wavelengths of light, which is important because hotter stars don't even give off very much of their light in the visible spectrum. Most of it ends up being in the ultraviolet spectrum. So if all we do is visible light, we can miss out on a lot. Okay. Luminosity is related to absolute magnitude, but it's not quite the same because absolute magnitude only includes visible light. The brightness of a star is how much power per unit area we get from it here at Earth. And we're a distance d away from the star. So we can set up a detector, find out how much light we're getting from it. We can have detectors that detect other parts of the electromagnetic spectrum, not just visible. For this, it might be helpful to have the detector be in space, so it'll catch the light that doesn't get through the Earth's atmosphere. But the luminosity, the brightness that we get, is actually equal to the luminosity divided by 4 pi d squared. Now, the reason that 4 pi d squared down there is that the light from a star goes out in every direction, and it's spread over a sphere when you're at a particular distance from the star, the light from that star is distributed evenly over a sphere that's equal to the surface area of a sphere of radius d, where d is the distance to the star. Just imagine a giant sphere surrounding the star, and the light from the star is spread over that entire thing. And 4 pi d squared, or 4 pi r squared, is the surface area of a sphere. So the brightness we receive would equal the luminosity of the star divided by 4 pi d squared, where d is the distance to it. Then, if we know the distance to it, we measure the brightness and we can determine the luminosity of the star. So, very powerful thing to know. And luminosity also depends on temperature. The luminosity of a star is going to equal the star's surface area times how much light it gives off per square meter. And from the Stefan-Boltzmann law, that F, sigma t to the fourth, that's the power it gives off, or the total energy it gives off per square meter of surface area per second. Energy emitted per second, which is power. The total power emitted then is going to be the luminosity. That'll be sigma t to the fourth times the area of the surface of the star, and sigma t to the fourth will equal 4 pi r squared. That's the area of a sphere, where r now is the radius of the star. So if we can measure the luminosity of the star by one method and measure the temperature by another, we've got a few ways to measure temperature, then we know the L in this equation, and we know everything on the right here except the radius, and we could figure out the radius of the star by studying that. So already we know a whole bunch of different things about stars. We can determine the surface temperature. We can determine the elements present in it. If we measure the distance to it and measure the brightness of it at our location, we can find out the luminosity. Then we take that, combine it with the temperature, and we can determine the radius, or the diameter, of the star. So we don't have to have them be anything other than pinpoints. So here's a bunch of different things that we can get so far by studying starlight. We can get the parallax. We have to do some observations for that, maybe on opposite sides of Earth's orbit. The distance in parsecs is 1 divided by the parallax angle, if we measure the parallax angle in seconds of arc. And so we can get the distance by measuring the parallax. Then we get the apparent brightness, combine that with the distance, and we've got the luminosity of the star, the total power output. Then we can study the spectrum. Some of these things we'll have to talk about a bit more, but we can get the chemical composition from that. Spectral type is something we'll talk about later, but we can get the surface temperature of the star. and combine surface temperature with luminosity, and we can get the radius of the star. So that's a tremendous amount of things to be able to know. Okay, when we do that, some interesting things show up. This is a somewhat baffling graph, but I want to have you get an idea of what it means. We have absolute magnitude running along the bottom axis here. And here's -5, which this would be a very bright star. 0, 5 is about the absolute magnitude of the sun, approximately, and then go up to 10 and 15. So we're going dimmer as we go from the left to the right. But we also have luminosity up here. And in the units we use for luminosity is an L with a circle with a dot in the middle of it. That happens to be the luminosity of the sun. We use it as kind of a yardstick for measuring luminosity. Okay, the brightest stars, the ones that are down here at -5 or -6, have luminosities of 10 to the 4th. That's 10,000 times the luminosity of the sun. Actually, there are some with 60 or 100,000 times the luminosity of the sun, which is amazing. And then this would be 10,000 times the luminosity of the sun. 10 squared is 100. This would be 1 times the luminosity of the sun. So if we drop straight down here to the 5, that's the absolute magnitude of the sun. So those two can be used either way, although luminosity is more informative. And then we've got stars that are 10 to the -2. That's 1/100th the luminosity of the sun, or 1/10,000th the luminosity of the sun. Now, there are various ways luminosity can fall. It can fall if the surface temperature is low, but it can also fall if the star is small. A very hot, bright star that's really small still isn't going to give off a lot of light. It'll give off a lot of light per square meter, but it doesn't have very many square meters on the surface. So that's what the horizontal axes measure here. But this vertical axis here is something kind of amazing. It's the number of stars in 1,000 cubic parsecs of space. Now, 1,000 cubic parsecs is going to be a cube that is 10 by 10 by 10 parsecs, or 32.6 by 32.6 by 32.6 light years. But something this graph tells you is that since it drops way off here when we go toward the bright end of the spectrum, high luminosity and high absolute magnitudes, this tells us that very luminous stars are rare. This is 10 to the -4th stars per 1,000 cubic parsecs. What that means is you'd have to have, on average, 10,000 of these 1,000 cubic parsec things before you had one star that was that bright. Okay. And this would be, you'd have to have 1,000 such cubes. Up here, you'd have to have 1 such cube. On average, you'd find 1 star of luminosity, this is probably around 70 or 80, in each 1,000 cubic parsec chunk of space. And over here, you'd find 10 on average stars in that 30 or 10 by 10 by 10 box of there. And low luminosity stars are quite common. Okay, so that's something important. And one more look at this. This is something called a Hertzsprung-Russell diagram. And we will learn a bit more about it, but I want you to start looking at this thing. This axis right here, this OBAFGKM, is a spectral classification scheme that they started. At one time, it was actually an alphabetical order, But then they realized on further study with these things that this axis, if you go not in alphabetical order, but in a different order, it turns out it's a temperature scale from the very hottest stars, O, over to the coolest stars, M. And there are actually some that are cooler than that. And so, and then the scale it's running along here is the absolute magnitude scale, which could also be the luminosity scale. Up here is an absolute magnitude of -10. Those would be the very brightest stars or the highest luminosity stars. And then down here is absolute magnitude 15. These would be very dim. The sun would be right in here. But something to notice, the very hottest and brightest stars, there are so few of them, they don't even show up on this vertical axis. This thing has stars per million cubic parsecs. A million cubic parsecs would be a box 100 by 100 by 100 parsecs, or 326 by 326 by 326 light years. That's a huge box, but the brightest and hottest stars still don't even register. And the stars that do register are red dwarfs. These are the coolest and dimmest stars, and there are more of them than any other type of star. They're by far the most common, but they're so dim they weren't studied until fairly recently. When I took astronomy in the early 1980s, our book didn't even mention red dwarf stars. They hadn't even been discovered yet, or if they hadn't worked their way into the astronomy textbooks yet. So that's something else to keep in mind. Okay, we will stop here. And there's a part 2 to this recording that I may get recorded tomorrow.